All right, so our next topic is going to be about logarithmic functions. So same thing, let's take a look at our learning targets, understanding the relationship between an exponential, which we studied last time, and a logarithmic function, converting back and forth between the two, basic requirements and properties. We're going to look at the graph of a logarithmic function, evaluate logarithms, and understand what a common logarithm is. So before you watch, go ahead and write down what you do or do not remember about logarithmic functions. Go ahead and pause your video. All right, so as a heads up, you will want your calculator for this video, so if you don't have it out already, you should maybe grab that. But we're going to start by finding the inverse of this function f of x equals 3 to the x. So if we think back to finding inverses, we had 4 steps to finding an inverse, and that first step was replacing our function notation with a y. And then our next step was switching our x's and y's. And then after that, we were supposed to solve back for y. Well, looking at this, I kind of get stuck, because how do I get that y down out of that exponent? I can't take a y root, because that doesn't really help me. I can't isolate y in this sense. So instead, for right now, I'm going to rely on my other concept of an inverse, which is the reflection over the line y equals x, because in this step right here, what we just did is we replaced our x's with y's and our y's with x's. So we were doing something about this line y equals x. So thinking about my original function, in goes, let's say, 0 and 1, out would come 1 and 3, right? Because 3 to the 0 is 1, 3 to the first is 3. Well, that means on the inverse, if I switch these, 3 to the x is my y value. So in goes 1 and out comes 0. In goes 3 and out comes 1. It's this switch around of y and x. So here's my red graph. This is something we looked at in a previous video. We had that nice exponential curve. So then when I go ahead and plot the purple graph, I'm going to go with the point 1, 0 and the point 3, 1. And I know that I've got to mirror this in the same way. Well, on the red graph, we had a horizontal asymptote at 0, which means that on the inverse graph, I'm going to change that y to be an x, and I have a vertical asymptote at x equals 0. So our generic log function, regardless of what this base is, okay, we're going to think about our logarithm function, this purple function, as always going through the point 1, 0. And then it's going to go through the point base, comma, 1. So in this case, our base was 3, because we had 3 to the x. In other cases, we might have different bases. So our function might be a little bit taller, might be a little bit shorter, so to speak. But we're always going to have this vertical asymptote at x equals 0. Our domain is only going to be from 0 to infinity, because that had been the range of our exponential. And our range then is going to be negative infinity to infinity, because that had been the domain of the original. So you've got some space to write down some of that stuff with our graphs. We'll look more at graphs of logarithms in just a little bit. But a logarithm is a form of an exponent. More specifically, though, we would say that logarithms and exponential functions are inverses of one another. So they hold inverse properties in the sense that their domains and ranges switch when you reflect over that line y equals x. An exponential function you're raising to a power. So a logarithmic function, you're asking yourself the question, what power? And we do this little switch around. So we looked at exponential functions, y equals b to the x, which means that its inverse function is that to solve for x, we're going to take a log, in this case a base b, of our y value. So if I know that 25 equals 5 squared, that means that 2, the exponent, the power, is equal to log 5 of 25. or I can ask myself the question, 5 raised to what power gives me 25? All right, so let's practice this what power concept. So use the definition to evaluate the following. So we want to take log base 4 of 16. So I need to ask myself the question, 4 to what power gives me 16? Well, that's going to be 2. Stay with me. This one, log 2 of 64, because I'm plugging in 64 for my x values, saying 2 to what power gives me 64? Well, that's going to be 6, because 2 to the 6th equals 64. So you can say this is, what power, f of x, 2 to that power has to give me 64. All right, so this one, log 5 of 1, says 5 to what power gives me 1? Well, that's going to be 0, because any base raised to the 0 power is going to be 1. This one then, log 3 of 1/81st, says 3 to what power gives me 1 over 81. Ooh, this is tricky. Well, I know that 3 to the 2nd is 9, 3 to the 3rd is 27, 3 to the 4th is 81. Ooh, 81, that's going to be helpful. So if I know that 3 to the 4th is 81, think to yourself, how could I get this to be the reciprocal? Hopefully you're thinking back to the last video, and if we take it to a negative exponent, that means we would get 1 over 81. So what power am I looking for? I'm looking for -4. And so it seems like we're kind of making up the system, right? Like we're rearranging these things that we already knew to be true. And the thing is, you're kind of right, because logarithms were invented as a way to undo an exponential, or to get an exponent down, or to think about it in a different way so that we could work more with our exponential functions. All right, so write the logarithmic equation as an exponential equation and solve for y. Well, an exponential equation we know has to look something like this from our previous video. So using that concept, I'm going to say 2 to what power equals 16? Well, 2 to what power is 2 to the 4th, right? Because 2 to the 4th is 16, and that means that y has to be equal to 4. Here, 2 to the what power? 2 to the what power equals 1/2. Well, 2 to the what power, 1/2, I know I could write as 2 to the -1st, which means that y has to be equal to -1. This last one's a little bit different. We're going to go y to the 5th. Y to the 5th power equals 17. And now to solve for y, I don't need to rewrite with exponents to match our exponentials. Instead, to get rid of raising to the 5th power, I can just take a 5th root. And that's my final answer. Okay, these ones, again, the variable ends up in the exponent. Here, our variable was a base, so we use a root to undo that equation. All right, so some properties of logs that we want to make sure we are aware of. First of all, log b of 1 is always going to be equal to 0. And the reason for that is because b to the 0 is equal to 1. b to the 0 equals 1. Here, log base b of b is going to be equal to 1, and that's because b to the 1st power equals b. b to the 1st equals b. It's this little swing around that we've got going on. Here, log base b and b are going to cancel each other out, and we're left with just x, which we'll investigate a little bit more later. Here, we have b raised to the log b. Well, an exponential and a logarithm are inverses, so those inverse operations will cancel each other out, and I'm left again with just x. And here, if I have log b equals log b of whatever this input is and whatever this input is, that means that x has to be equal to y. Because if you're taking a log of each of those numbers and they're coming out the same, that means that the original inputs, the x or the y, had to be equal to each other. These are going to be super, super important. Study these, learn these, know these, right? And they come from our properties of exponents that we've worked with before. All right, is there a log that perhaps appears more often or is more useful than other logs? The answer is yes. And we talk about 10 or a base 10, which we call a common logarithm. And so we could write log with a base of 10, or sometimes we write it as just log, and it's implied that there's a little 10 there. So if you look at your calculator, over on the left side, we have a log button that is assumed to be log base 10. When you are using that button on your calculator, that is a log base 10. So using your calculator, go ahead and evaluate these 4 expressions. So I'll help you get started. If I want to do log 10 of 100, I can press log. Maybe my calculator will let me. Oh, too many logs. Log of 100, which is 2. Now that should make sense because what you're saying is 10 to what power is 100? Well, that power would be 2. So go ahead and type in these other 3 into your calculator and see what you get, and we'll compare answers in just a second. So pause your video. All right, hopefully we got to this point. I want to talk real quick and I want to focus on each one of these kind of for different reasons. So this one again, 10 to what power gives us 100? Well, that's the same thing here. 10 to what power gives us 2/5? Well, we know if we're going to get to something that is less than 10 to the first or 10, we're going to need this negative value to get us a smaller number. So it makes sense that this one comes out negatively. Here, this is 10 to what power gives us 5, and you might think that there should be a nice relationship here, but 10 to the first is going to be 10, 10 to the second is 100, 10 to the third is 1,000. 5 is definitely lower than all of these things, so it makes sense that our log value is going to be, or our exponent value at the end is going to end up being something less than 1. Here then, we're asking ourselves 10 to what power gives me -4. So it makes sense that we get a non-real answer because is there anything you could raise 10 to that would end up creating a negative value? I mean, we know 10 to a positive decimal gets you positive number. 10 to a negative decimal is getting you a negative number. 10 to the 0 is going to get you 1. So trying to figure out why this is happening, we can look back at our graphs. So I can think about this in 2 different ways. I can think about the graph of 10 to a power. Well, 10 to a power is going to go through that point 0, 1 and the point 1, 10, and it's going to be our exponential graph, 10 to the x. Well, that had a horizontal asymptote at y equals 0, so it couldn't ever drop to be negative. The other way to think about this is from the logarithm graph. And what we learned in the beginning of this video is that our logarithm graph goes through the point 1, 0 and has a vertical asymptote at x equals 0, which means can we put in a negative number into this function? Well, no, because our domain is only from 0 to infinity, and -4 is not between 0 and infinity. Again, we'll continue to make these connections back and forth, but if you stop and think about a logarithm is an exponent. It's what power, what power, what power. Things will work out a lot more in your favor instead of trying to get too caught up in this logarithm concept. I'll leave you with your questions for understanding, and go ahead and try to jot down some answers to these. If you have questions for your teacher, these would be a good way to start those conversations the next day in class and maybe ask for some clarification. But realistically, we're working back and forth between exponents and logarithms, exponential functions, logarithmic functions, and understanding that they are inverses, and you are asking yourself what power when talking about a logarithm.